So welcome back, everyone. So it's a pleasure to listen to the next talk by Rémy Mahfouf on the near critical FK percolation. Rémy.
Okay, thank you very much. Thank you to the organizers. Thank you to the organizers for this beautiful conference. So today I will talk about kind of something in the middle of two of the mini course you saw last week. So you saw a mini course by Ioan Manolescu about the FK percolation model. And I will try to discuss a bit of this FK percolation model in random environments. And what happens if, like, first I try to kind of sample randomly my environment, and then I look at an FK percolation model in that random environment. And one of the specific cases of the FK percolation is the Ising model. And the Ising model fell into the kind of class of like something called S embeddings, which was presented by Dimitri Chalkak. And actually, there is actually a similar version of that. So the kind of long-term story is that, okay, there is also a way to construct like random embeddings. And the kind of this is two sides of a similar story. And I will try to explain it and promote it. So it's a joint work with Emile Averus, who is a PhD student now in Geneva and who is on the left in the picture. So I will go back to just very basic explanations on percolation. So like the easiest model we're going to discuss is the planar bond percolation. So you take a subgraph of Z2 and you fix a bond parameter P, which is uniform for entire lattice between 0 and 1. And then you open independently edges from each other with probability P, and you close them with probability 1 minus P. And you get like a picture like this. You get a picture like this, and you get like, a random graph of Z2, random subgraph of Z2. And then what's the probability of a configuration? Actually, it's proportional to P to the number of open edges, 1 minus P to the number of closed edges. The kind of scaling factor, which is going to be like important in our setup, is going to be like the partition function, and this will play like an important role. The second toy example actually is the Ising model. So I will take like slightly dual convention, and I will say assign spins to faces. My graph. So each face I'm going to assign like a plus minus 1. And actually, I'm going to fix a kind of an X parameter between 0 and 1. And X is going to be like the cost to having non-aligned neighbors, like to having two disaligned neighbors. So in particular, in that case, in that specific case, the probability of like a spin configuration, and here it will be like important, is going to be proportional to X to the number of like disaligned spins. And basically, what's going to happen is that depending on the value of X and before depending on the value of P, you will have like very, very different behaviors of your model. Like it's going to be like a competition, for example, for the Ising model between entropy and energy. And you will try to see, like, depending on the value of X, what more or less is the behavior of the model. But what's very interesting is that when our goal would be to take like those X like independent and random at each edge, right? And to see whether we can does it still look like critical or not? And up to which extent it still looks like critical. So as Ioan explained last week, there is a phase transition for percolation. So for percolation, you have like a critical value at P equals 1/2 on Z2. So that's one of the very few lattices where you can compute explicitly like what is the critical value of the model. And you see, like, I'm gonna be like looking at what happens around P equals 1/2. So I'm going to look at something called the correlation length, or like the characteristic length is like, okay, imagine I move a bit from 1/2. So I move here from 0.01. And if I move like slightly upwards, slightly downwards, I'm going to have like very, very different behaviors. And that will be like a kind of saying, kind of an explanation on like why, on like what happens near the critical point. So this phase transition actually is actually non-trivial. There's like many computations which were made, and what is very interesting here is that this picture, I'm not sure it has been that that much explained. I mean, it was mentioned, but is something called conformally invariant, right? So really, like here, you have kind of mixed behaviors. You have basically clusters. So here, like clusters are given in color. You have clusters of like macroscopic size of the box, macroscopic size with respect to the size of the box that coexist with each other, right? Really, like here, you have one big cluster. Here, you have like a lot of small clusters. So yes. So here, typically, if you have a box of size n, I mean, here you're gonna have like clusters of like radius n, here of logarithmic size, and you have like here one big cluster which almost eats everything. Same for the easing model, you're gonna have like a phase transition. So at the parameter x in our parameterization that I gave before, the critical parameter is gonna be like square root of 2 minus 1, which is actually a self-dual parameter for the correct parameterization. And if x is very small, actually it's gonna become super costly to have disaligned spins. Right. So typically what I'm showing here is something called the Brownian boundary condition. So here I did impose plus on the bottom, minus on the top. And I basically want to see whether the kind of boundary condition they translate inside. That's kind of an important statement. Here, basically, like they decorrelate very fast. So like basically spins here, they're kind of plus minus 1 with probability 1/2. And there's kind of an exponential correction with the size of the box if you're in the middle. Here, really, like the boundary condition, they win. It becomes super costly to just basically have like to break the symmetry. And here, like I think typically the fluctuations in that line are like of order square root of the size of the box, so it's kind of an almost flat interface. Now, okay, you can, as you see, as you saw, like in different talks. I mean, we were discussing like. What we discussing? Yeah, we were discussing like big boxes, but actually you can even play it in the full plane. So you can try to have a discussion or to try to align and impose like plus minus spins, but like in the entire plane, and that means that you need to construct like a full plane Gibbs measure. You need to construct a measure in the full plane because after all, I mean, this renormalization, I mean, the way you were constructing your probability measure, you had to normalize by something, and it's definitely not trivial. To understand what's happening. Like maybe it's a bit more complicated to define the measure in the full plane, but actually the physics helps you a lot because in many ways, I mean, if you look at, for example, the magnetization of one given spin, if you just push the plus boundary condition, say further and further away, you decrease your magnetization. So that means that like you have a natural monotonicity, so you have a natural way to construct like to construct a full plane measure. The thing is that one of the first important quantities actually, and that's one of the key points to look at, was something called the free energy. So you basically take the log of the partition function and you just divide it by the number of vertices in your box. And actually, this is a function of x, so for the original x parameter. And this function actually is like C infinity. It's a C infinity function, and actually it blows up like it's C infinity except at the critical point, and there it has like a second order phase transition where basically the first derivative is well defined, but the second derivative blows up like logarithmically. So this is like very old results, and well, okay, those are kind of foundational results, and they try to kind of explain on that was one of the first models in StatMech that was really studied in such a way, and basically compared to other FK models that I will discuss afterwards, this one is very, very special. I mean, it's very, very integrable, and you can run much, much more computations. Now, okay, so basically the easing model and the percolation model, actually they interpolate. So they kind of belong to a much bigger class of models, which called like FK percolation, which is known, which was explained by presented by Johan last week. And then basically you take the probability of a configuration, p to the number of open edges, so it's still like a random subgraph, q1 minus p to the number of closed edges, but then you basically add an additional term, which is q to the number of clusters. Right. So what does it mean? It means that basically I was taking my kind of Bernoulli percolation model, but I was twisting it by q to the number of clusters. And basically, when I have like one cluster alone, at one point alone, it's basically like considered as a cluster. And roughly speaking, I mean, you can try to study. So Q equals 1 is basically percolation, and Q equal 2, it's something called the FK easing model. And you can basically, once you just run the model Q equal 2, you can run an additional like plus minus 1/2 independent coin on each connected component, and then you get like classical. Okay, the kind of important model. So I will be working always for Q bigger than 1. Because like for Q bigger than 1, I mean, you have something called a model of positive association. And what does it mean? It means that like connected event kind of tend to favor each other. So what's the probability to have, for example, like the two paths connected between 2 points? Actually, it's bigger than the product. It means that the conditional probability, if you already know that Z is connected to T, you have a bigger probability that X is connected to Y, right? So really, like it's a model that favors connections. And that's actually, you can start discussing, and that's very important stuff because I did not mention that much, but you can also discuss like 2 kind of boundary conditions. So you can just look at your box, and on your box, actually, you can just impose that all in your measure, all your external vertices are just connected to be like one vertex, right? That's the wired boundary conditions. And then you have also the free boundary conditions. The free boundary conditions is basically the boundary condition where you leave independent, like, okay, you don't force connection between like boundary vertices. What does it tell you? This model is a positive association, which means that if you look at the connectivity property between X and Y, it's higher actually in the wired model than in the free model. And the reason behind that is that basically you can like basically try to use the boundary clusters. Actually, they really help you. They really favor you, your boundary conditions. And well, okay, I was discussing like passing to the full plane, and actually, if you want to pass to the full plane, it's difficult a priori because it might happen. Like you can pass to the full plane for the free measure, you can pass to the full plane for the wire measure, but it's definitely not clear that you're going to get the same stuff. But actually on Z2, if you fix a Q, whatever P, the Q between 1 and 4, is going to be important. Whatever is the P, then you're going to have like one infinite ergodic Gibbs measure. Note that like one of the very, very interesting questions, which I believe has very poor treatment, is like for Q is smaller than 1. So for Q is smaller than 1, I mean, we still expect to have like nice result at the critical point, which I will discuss afterwards. But there it's a model of negative association. So the kind of connection, they kind of tend to unfavor each other, but still, I mean, you expect like to have a very nice limit at the associated critical point. And okay, I mean, it's still an interesting discussion of like, okay, I showed you like pictures about this phase transition. Now let's try to make it slightly more quantitative. And this phase transition is called sharp. So there's a result by Beffara and Dumini-Copin. I think it was also, maybe this requires like an improvement with the Sidor-Avicius, which was made years later, depending on what you take. But basically, I mean, you can try to look at the box of size n by n. And your box of size n by n, what you do is that you impose that all the top vertices and all the bottom vertices, they're connected together, right? So you have like one top arc, one bottom arc. And you can try to look at what's the connection probability, like what's the probability that you have a path from top to bottom, right? And the thing is that if P is smaller than the critical value, so like critical value is actually a self-dual value, which was derived it was guessed like a while ago, but like there was a rigorous proof by I think it was guessed like in the 80s or in the 90s. But like the work of Beffara and Dumini-Copin, actually they really proved like this kind of dichotomy of behavior. And here obviously like I'm wrong, but so it should be like bigger. So if P is small enough, so smaller than this critical value, I mean the probability to have a long path actually decays exponentially fast in the distance. If P is bigger than this critical value, well, the probability to have a long path goes to 1 at exponential rate. And what's going to be interesting is this kind of PC critical value of Q. And here, basically, the probability to have a top to bottom path is, is bounded away from 0 and 1. So there's like uniform constants which do not depend on the size of the box, such that you have like the probability to have a top to bottom crossing. So that's like basically that's the sharpness of the phase transition, and that's really like you really have three different critical phases. And what we will be interested in actually is like what can we do around this PC of Q? Like what happens when I start moving P around PC of Q depending on the size of the box? And if I do that, well, basically, do I get something which is interesting or not? So what do you have? So, okay, this stuff more or less I explained already. So like the distance, so this stuff I explained already, like really like you can be at the same distance from the critical point, but have like really different behavior. So the sharpness phase transition. And okay, now we will be focused for like 1 or 2 slides actually on that, on what happens exactly at this critical picture. So what was proven, like in a paper which dates back to 4 or 5 years ago, is that if you look at this full plane picture, so you pass to the full plane and look at this picture, I mean, you get something which is rotation invariant in the limit. And actually, as Johan discussed, this joint work with Piet and Carol, actually, you can construct a 6-vertex model out of this critical model. And this model has like GFF convergence, but still like only in the full plane. And conformal invariance in many ways is something which is very much related to bounded domains. And well, okay, I think there is hope that at some point people are going to be able to do that. But in general, I mean, like having better understanding of this picture than this box crossing property is something very difficult. What do you expect? So beyond this full plane discussion and this full plane picture that you were given, you expect something else. You expect like not only box to box crossing probability to remain bounded away from 0 and 1, but you expect them to converge. And you expect to converge to some very nice object, which are conformally invariant in the limit. So I will explain that. So typically, like take a domain, take a shape, right? And you discretize it with the domain of mesh size delta, so of size 1 over n. So you really like take your Ising model on a shape like that. And what you expect, which was checked by numerical simulation, which was predicted by CFT physicists, that as delta goes to 0, you have a scaling limit. That your discrete model looks like a continuous model, and this continuous model has correlation which are described by CFT. And what does conformal invariance mean? It means that if you take a domain and you take the scaling limit, and if you take another domain and you take the other scaling limit, well, the way the scaling limits are related is exactly by the conformal map that sends the first domain to the second domain. So that's kind of the ultimate goal. Like would be like how to completely the picture, like to have a full understanding. And actually, we do not have a full understanding of that, except for a very specific case of the Ising model. The rest, I mean, and the site percolation for site Bernoulli percolation. Except that, I mean, this kind of behavior which is predicted, I mean, still not proven. So you have works basically, I think, by Smirnov, who are kind of the only works who settle down everything properly, but still, I mean, and you have works by King and Weimers, but typically, I mean, trying to arrive to this level of understanding is something extremely difficult. Still, for the Ising model, I mean, as you saw, I mean, most likely in the mini course, I mean, the Ising model is something very integrable. It can make much more computation, and you can say many things. So what you can say typically is the following stuff. So if you take a domain, so here it's a square, and you take basically the leftmost interface between the pluses and the minuses. So if you attach 2 boundary points, A and B, and you can try to just say, okay, I have an interface that separates pluses to minuses. Those are like discrete interface on the grid of mesh size delta, on the grid of mesh size 1 over n, right? And the thing is that this family of interfaces actually converge to SLA3. And that's one of the, so you can really identify the limiting family of interfaces. Now, if you look at the associated FK model, you can even prove that like the interfaces converge to SLA6 over 3. you can look typically at what happens. It happens like if you not only look at one interface, but at the entire loop of clusters, entire soup of clusters, and this will converge to like the nested CLE tree. And you can even say more stuff, like you can try to study correlation functions. So you can basically fix here 2 points in your domain and try to say, okay, if the 2 points in my domain are in that position and I scale properly by the delta to the correct power. Yes.
Quick question. So how are these results related? Can you deduce the correlation function convergence from the CLE3 convergence?
Okay, so it was not known up to very recently. There was no proof, I think. There is a proof by myself in a paper for periodic graphs. You cannot deduce fully. You still need to know like the one-arm exponent. You still need to know like the probability to connect far away. But yes, I mean, it's a very recent proof that I put on the archive, but either way, it was not exactly like that. I mean, the kind of, there were really like some specific observable techniques that were really allowing you to reconstruct more or less by hand, by integrability, all the correlation functions. So you kind of say, you were saying that, you know, correlation function, they're related to some discrete analysis problem, and then you were solving the discrete analysis problem. But yeah, I mean, generally speaking, yeah, it was not known up to very recently. There's also work by Kamiya and Feng, I think, which kind of have a similar idea. But actually, this is like really different works. Okay. Now I will just, now that I talked about like more or less kind of classic stuff, I will try to kind of convey an important message, which is something that is very dear to me, which is something called the near critical models. What's going to happen is that I'm still going to be under my box of size n by n, but I'm going to just take my critical parameter and I'm going to perturb it by something that goes to 0 with the size of the box, right? And I will do it in such a way that I have a meaningful and non-trivial scaling limit. What does it mean? It means that, for example, for percolation, you take your critical value, which is 1/2, then all the edges, you just add them 1/n to the 3/4. This is like something which is, this is a specific power. For easy model, you take like your critical points and you add 1/n. So really like it's different models. So since it's different models, I mean, they have like a different power here. So you do what we call a massive perturbation. So it's a near critical perturbation. So you scale the temperature as well as you scale the lattice. And what's very, very interesting there is that in that regime, I mean, you will get new results. So you will typically want to prove results similar to that, but actually it's not that trivial. But you will get like a scaling limit, typically in the sense of what's explained here, but which is going to be different. So I will first like discuss the percolation model. The percolation model. So there's an absolutely beautiful paper by Nola and Werner, which says the following stuff. You can look at like, okay, percolation triangle lattice. It's a bit, I will discuss this afterwards, but you perturb your model by exactly that amount. And what you get is that the family of curves that you obtain in the limit, so the kind of curves separating like open and closed edges, well, there, I mean, it's non-trivial. It has the same Hausdorff dimension as the critical SLE6, which is the limit on the critical square lattice, but it's not absolutely continuous with respect to the SLE6. So you really get the scaling limit here, which is not absolutely continuous with respect to the critical model. So you get something which is different. Actually, you have really like a different kind of scaling limits. The only other places where people were able to kind of study those kind of scaling limits were dimers. So there was original work by Sunil Shita who just look at like perturbation, and then you don't get a GFF in the limit, you get something more complicated, like the correlation functions, they're just not those of the GFF. You have like some work by Dima Chalka, Konstantin Zorov, and myself, also by Sushulkar, where basically we compute the near critical correlation for the easing model. So they're expressed in some weird way. So they're expressed as solution to some discrete analysis problem, but to some continuous analysis problem, but basically, I mean, if you perturb by that much, you get a meaningful non-trivial limit. Yes. Yeah. Yeah, I allow minus. It's very important. So that's the order of magnitude. And actually, if I put 1, but here I put 1. But imagine I put 10, I will have a different scaling limit, right? It's going to depend on the mass, m over n. And will have a continuous family of scaling limit here that's going to appear. So the overall takeaway message is the following. So if you perturb, you get something which is different, which is not a priori absolutely continuous with respect to the result, but it cannot be like the same limiting process. But what's still interesting is that for those near critical models, you still have this box crossing property. You still have crossings. Still have probability to have long paths which are bound away from 0 and 1.
So can I just ask, this box crossing property, don't you expect it only for boxes within the correlation length or something like this? Like
yeah, no, this is kind of within the correlation length hidden.
It's on lambda n.
Yeah.
Sorry, yeah. Also, what do you mean by largest deviation to remain within the critical phase?
Basically, you cannot. So basically, if you took log n over n to the 3/4, you become off critical. Like you really have, that's, if you take something very small compared to 1 to n to 3/4, you have the same scaling limit. You don't see anything different. If you take something much bigger, you have the enough critical scaling limit. And exactly at that order of magnitude, you have something in the middle, which is a different scaling limit. Okay.
Scaling window for percolation based on the forearm exponent, right?
Yeah.
But is there a way to see it for easing?
I will discuss this at the end. So the kind of way to see the scaling limit for I will discuss this more or less. There is a geometric way. It's in my recent paper on kind of embeddings, which basically tells you that if you perturb all your complete constants, you should start with like a nice embedding of the square lattice, like an SAS embedding of the square lattice, of which I'll have to express. You start perturbing, and you can construct a non-trivial, non-degenerated embedding with this. This is the order of magnitude where you start seeing your embedding change. So it's not that easy. The special case, I will discuss afterwards what you can do, but this is really related to like the iota exponent that will. Anyway, so that's not trivial. Now, let's try to discuss the notion of scaling window for percolation. So imagine I'm on the box. So before, like here, what is gonna play the role of 1 over n to 3/4 in the cases where I have no integrability, where I have basically no option to make exact computations, right? What is gonna play the role of that, where when I don't know like what's the scaling limit at criticality, so I cannot say more stuff. And what's gonna say what is gonna be like our setup is gonna be something we're gonna call the critical window. So this was introduced actually by in the formalism by so I'm going to discuss now formalism of the paper of scaling relation between Manolescu and Copain. So what is the scaling window? So I fix some delta, which is a fixed number but small enough, say, and the W of n, the critical window with respect to delta, will be like the biggest deviation I can allow from the critical value, such that in one of the squares inside, my crossings, they start to become very close to 0 to close to 1. So one of my crossings, so before, like at criticality, I know that all my crossing in sub boxes actually were bound from 0 and 1, away from 0 and 1. And my critical window, the way it's going to be defined, is going to be like how much, it's going to be how much I can deviate on the box of size n, such that one of the square really starts to become off critical.
Oh,
yep.
Just to check, so the PP is your unique infinite volume measure here? Or
yeah.
Yeah.
But here I really look on and so this is, in many respects, this is an off critical statement, right? W of n accounts for like value for measures which are not at criticality, right? A priori, you look at like models with different parameters than the critical. You can define also some other quantity, which is actually the mixing rate. which is actually at criticality, what is the probability that you connect from 0 to the side of the box with wired boundary conditions minus the same probability with free boundary conditions. So typically, I mean, for the Ising model, I mean, this is probabilities of order 1 over n to the 1 over 8. This also is 1 over n to 1 over 8. But when you take the difference, you have something of order 1 over n. So it's something very small. It doesn't make sense for percolation, actually, because like, just sort of thing. But in some respect, you have this off-critical quantity, which says by how much I can deviate from my original model without just breaking my crossing probability, making them too close to 0 or 1. And then I have this very critical probability quantity, which sees how interesting is it, how influential are wired boundary conditions compared to free boundary conditions. And then there's this beautiful, so there's like a lot of stuff in the paper. One of the beautiful relations which is proven there is something called that scaling relation is that n squared W of n it's asymptotically equal to delta of P. So that basically your mixing rate, so you're off critical, so your probability to connect at criticality is basically connected to like how much you can deviate off criticality. Right? So this is really like a deep statement. Okay, so this is interesting. And what was proven in that paper by Manonescu and Rémy Copin was the following: is that basically if you did not deviate too much from your critical window, so if on the box of size n by n all your edges didn't move by more than like W of n, well, you still have a model which very much looks like the critical one, but not only for crossing probabilities, but for all the kind of much more subtle events. So the probability to connect, so the arm events, they remain the same, the mixing rate, they remain the same, and the covariance between edges, they remain the same. Yes,
Yeah, hello. Yeah, just to check, when you talk about the crossing probabilities, and I mean, are you in full plane or are you in?
No, I'm in boxes.
You're in boxes with the worst boundary condition.
I will afterwards. We'll be in torus, so it will not be a problem anymore. But so the kind of conceptual message is that this near critical window, which a priori was just only defined for crossing events, so macroscopic crossing a priori. Well, actually, it tells you that if you don't move regarding crossing events, then you don't move for all the kind of very subtle properties of your model, of your connection probabilities that you can have, which is actually not true. So this near critical window, actually, it's expected to decay like a polynomial, but it's not proven. It's only proven like for percolation on triangular lattice and for Ising model. Either way, we don't know. Okay. So the conceptual message is here is that if you should be at order of magnitude W of n, you should have a non-trivial scaling limit. And if you just do bigger, you go off critical, basically. If you deviate more than that, your model looks like off critical. Okay. Okay, now let's go into what I want to, into kind of the main part of the talk, right? So here I rediscussed like what was the critical window and what was basically the FK percolation model. So I can try to replay the same model in torus. So I'm going to be now on the torus of size n by n, and I'm going to just basically take the same FK measure, but I'm just going to multiply it by square root of q. So for each cluster, I mean, I'm going to multiply by square root of q to the number s of omega, which is basically 0, 1, or 2. And the 0, 1, or 2 depends really on the topology of the cluster, like whether it has a homology class, dependent homology class of the primal and dual cluster in that column. It doesn't change much, but you have like a self-dual measure. Okay, so here now I'm going to a torus, so I don't really want to discuss boundary conditions. Okay, and this is where it's going to be a much more interesting statement. So I told you, like, if I were taking W of n, if I put absolute, so now for each edge, I'm going to take random, an independent random. Yes.
I just have a question about this scaling relation of Hugo and Mano. how is it possible? Isn't that telling you that the scaling window is always smaller than 1/n squared immediately? I'm confused. But for easing, you said it was 1/n. So
maybe I messed it up. Maybe it's 1/n squared. No. Okay, W of n is like 1/n, and it's also 1/n. No, it should be.
maybe you need the -1.
Yeah, I need
on
the
the right.
Yeah, I might have you might have messed up the.
Thank you.
Sorry. Yeah, most likely. Yes. The important part is really that like there is a relation between the critical and I mean, I'll try to correct. What? Yeah. Now, what I will do is try to just put some randomness. So now I'm going to sort my edges independently. Okay. So I'm going to first sort my edge weight, so my PE, and I'm going to do it in the following way. So I'm going to center them around PC, and I'm going to see by how much I can deviate from the original case if I just here like I put plus minus independent random variable, right? And the theorem, which we prove with Emil, is that if you take basically edges, which is like the critical value with plus minus the critical window to the power 1/3, which is actually much bigger than the critical window the original critical window, then you still have like a model which is in the critical term. And you can, so if you didn't have this plus minus 1/3, if you just had only pluses, it would just right away tell you that the model would be already like very much off critical. So really like that means that the randomness in the environment averages well enough such that with high probability with respect to the environment, I mean, you still have like a model which looks like the critical one. And this 1/3 exponent is actually optimal in the sense that like you really expect that if you just take center plus minus correctly centered and say what the W of n to the 1/4, then you will have like some boxes, like some crossing which is gonna blow up. So really like the model should become like off critical at least for some internal crossing. So here I'm really asking that in my torus, all my crossing probabilities in all my square become preserved. So we give a very strong indication that's the fact. We give a very strong indication that's the fact. If you wanted to have a full incomplete proof, I mean, you would have to basically go through like explicitly computing like third or fourth order derivative of some martingale and time variation processes, but like the heuristics really that they really blow up exactly that. So that's what you can do. So if you take like IID variables, and actually they do not, so here I did put plus minus, but basically you can take any center process. Okay, so they don't need to be IID. As long as they're independent and they're correctly centered around the critical value, you can basically perturb by like the critical window to the power 1/3, so much bigger than the original one, and randomness in the environment is going to average very well. That's the message. Okay. Now there is a second model that we introduce, which has an even bigger critical window. It's something that we call the corrected model. So you can basically deviate with plus minus 1 up to basically order 1/log n. But then you have to put a correction which is not an independent correction. So in some respect, I mean, if you put PC plus minus 1/log n, like you can find the correct random process actually, which is obtained by an SDE, which actually is correlated. So it means like it's not like independent. The edges of the law of the random law of two edges is not independent, right? They're slightly correlated in space, but this is like much smaller actually than 1/log n. And for that, I mean, actually, if your Q is between 1 and 2, you really get like you can go to 1/log n. So you almost reach like macroscopic scale. So that means that that's kind of the random correction you should put to have like a slightly correlated model, but like remain. So yeah, so in some respect, like the first layer of randomness, you can take everything independent, but if you just allow to be almost independent, like at least independent of first order, then you can go even to much bigger scaling window.
Can I ask? So why do you need that Q is smaller than 2? Is it related with the iota exponent being
Exactly.
larger than 1? Or?
Yeah, it's related to the iota exponent.
Okay.
Yeah, can I ask about the, so just to check, you have your model on a torus, it has the square root Q S of omega term. So that doesn't affect the deterministic scaling.
So really, if you, so the kind of conceptual message here is that if you allow yourself a bit of correlation in the first layer of randomness on how you sort your coupling constant, you can even do better, right? And then I will finish with how much time you have?
You have about 10 minutes. Sorry, can I just ask one more question? I'm a bit confused. What is this S omega term doing?
This one?
Yeah.
I mean, it counts for the kind of whether all the primal clusters have homology class 0, 0.
So this is counting like the winding of these clusters around the torus?
Yes. Well, so yes. And I will finish with the special case of percolation. So up to now, I mean, I was really thinking near critical scaling window. So really like I needed to scale something to 0 with the size of the box. And what we're gonna see is that for percolation, actually, you don't need to do that. That's the last theorem of the paper. So I think the easiest way to present it is the side percolation. So I discussed like a lot like bond percolation, but I can also discuss side percolation on the hexagonal lattice where I open independently the side. So I just I color them either blue or yellow with the probability P in blue, yellow in probability 1 minus P. And I still have like the probability of a percolation configuration, which is this one. So really like this is independent plus squares. And there is this beautiful theorem by which is due to Smirnov, which was guessed by Cardi first, is that if you take a triangle, so it's the simplest example, but if you take a triangle, you can look at what's the probability. So you take a big triangle of size n, equilateral triangle. What's the probability to have a blue path that connects the left to like that portion of size x of the bottom arc? And this probability actually it goes to x when n goes to infinity. So the probability to have like that's the problem to have like a connection event like this from this arc to a portion of size x is actually equal to x. So you can do it in actually more complicated domains and connect boundaries to boundaries, but that means that there is a very nice formula that you can guess and that you can find on like this probably to have like a specific random path arriving to a specific region. And you can even do better. So basically what was done like with SLE, similarly to like the convergence of SLE tree that I mentioned before, actually this was done like 10 years before that, okay, you have like the interfaces between blue and yellow, they converge to SLE6. So really that's one of the rare models where you can really say such a statement. Actually, if you try to prove such a statement on the square lattice, I mean, up to now, there's no proof. So it's very, very specific to like triangular lattice side percolation. And now, what is our theorem? So before I was excluding Q equal 1 for this near critical scaling. Well, if you just still look at your model on the torus, what you can do is that now without a random correction, like without correlated correction, if you put like you take independent random variable which deviate by at most 1 over log n from the original 1/2 value, and those plus minus are IID, you still have like your model which is critical at every scale. So really your box crossing property is preserved at every scale. So for percolation, I mean, the independence between edges helps you to just go even further. And now, but here, I mean, I'm saying that the criticality is preserved at every scale. That means that every single box here has a probability bound away from 0 and 1 to be crossed. But and that's the kind of final argument is that you can try to just do macroscopic deviations. So now imagine you just on the side percolation, you are on the side percolation on triangle lattice, like on the this kind of X lattice, and you take random variables which are independent, okay, which is centered at 1/2, but they're bound away from 0 and 1. So like they just if they are between like 0.99 and 0.01, it's fine. This theorem. So they don't need to be around 1/2. They just need to have an average 1/2. Okay. And so like the easiest way is that, for example, for the assigning the blue color in this kind of side percolation, you just can say, okay, in advance, I first toss whether it's going to be 3/4 or 1/4 with probability 1/2, and then I do a percolation model with this obtained environment. And then like the theorem, which is the final theorem of the paper, is that if you look at large scale, well, with high probability, the Cardi formula holds, right? So that it really like the percolation averages well, and so the difference between those two statements is that here you're going to have like small boxes which are going to break. So here you're really going to have like small boxes which are going to be like supercritical or subcritical. But if you start looking at like large scale properties, then okay, at least the Cardi formula holds. And I think, yes, and the kind of only message I want to convey is how can you go from here to there, and why is it blocking? Is it blocking to 1/log? Basically, what's happening is when you try to compute the derivative of a crossing, actually you have like 4-arm events which appear. Now, if you just put random processes, which is 1/2 plus like a Brownian motion, which is centered at 0, well, typically it's going to be like squares of 1-arm event which is going to appear, 4-arm events which are going to appear for percolation. And it's known that the 4-arm event actually has an exponent which is bigger than 1. It's supposed to be 5/4. And so what you have is that now when you're summing over your entire box of like something which decays like faster than 1/n², okay, you have something that goes to 0. And you could say, well, okay, maybe I could just try to run this argument everywhere. The problem is really that in order to apply all these techniques which are discussed in scaling relation, you cannot allow yourself that small boxes break. Like really, like if some boxes inside break, it becomes like a priori much more difficult analysis to make. Like the scaling relation paper is very, very much based upon the fact that every single square, whatever its size, is always going to be crossed with a good probability. And the thing is that you kind of need a renormalization argument telling you that, okay, if some squares, but not too many of them break, I mean, you typically keep such a bound. But when you do that, I mean, you just have a hint of noise sensitivity because like this is kind of squares of influences. And well, then this tells you right away that you should apply noise sensitivity argument. And then Emil found the noise sensitivity argument, like actually very cute. And that's a kind of cheap statement. Once you understood that, then you understood that, okay, this bound, you want to keep it running along your kind of deformation process, random process, but you really can't. I mean, still you have it at the beginning. So that's kind of the classical noise sensitivity statement. So kind of noise sensitivity condition. So that's how Emil found. And like basically this corrected model is kind of obtained in a similar way as here. So you basically introduce a corrected model to have like such that all the crossings are basically local modular. And that allows you to use like the fact that like iota exponents is like bigger than 1 to just conclude that you can go to 1/log.
questions.
So yes, I'm just confused by something. Is in the near critical regime, if the limit is indeed a massive SLE, shouldn't the Cardy formula break? And
No, it breaks.
and how is it compatible with the fact that here you have an average Cardy formula? Shouldn't it be something that
No, but like in the massive regime, I mean, you always go in the same direction. You always supercritical or subcritical. Here, like if on average you're 1/2, there time to time you're gonna be subcritical, time to time you're gonna be supercritical. It's just they're gonna average out each other.
So you mean that so the point is that the averaging of the subcritical together with the supercritical
Exactly.
gives a critical thing. But in that case, what should be the anneal limit of your model if there exists one? Should it be like a
For
true
this one
SLE?
is no. For this one is okay. It's trivially percolation. It took us like a couple of hours to see, but like, it's trivially like.
So you mean that if you are able to solve the problem, you will have an SLE in the limit. Okay. Thank you.
But having an SLE in the limit here is difficult because like if small boxes break and small regions actually become supercritical or subcritical, I mean, you don't really know what happens if the SLE just reaches that point. Like, what is going to be the local behavior? If you curve, it's the local.
Any other questions?
I think I missed something. Can you go back to your 1/3 theorem? I'm trying to understand. So here it's the same context as the Q = 1, but somehow you go from an exponent 1/3 to a log.
Yes.
What is going on? Like why does this happen?
This is a very good question. Imagine you do that. You just you take a random process, which is like the critical value plus a Brownian motion. So something centered around that, right? The thing is that, well, when you just compute like stochastic derivatives, you're going to have like a local martingale, which is going to be not the dominant term, and you're going to have a finite variation term. And the finite variation term is actually, when you estimate it, it's actually of order Wn to the 2/3. So if you can run, so that means you can run your stochastic process up to time Wn to the 2/3. So you're going to have something of order Wn to the 1/3. The thing is that for percolation, this stochastic term, this finite variation term simply is 0. In special case of independence, this kind of main dominant term just disappears. That's the thing. And actually, that's how we could construct the corrected model. We basically add the counter term to kill this finite variation process. If you kill the finite variation process, you get squares, basically. So you get like much better balance. That's the point. Like the independence of percolation kills like this kind of finite variation term, which is the main dominant term. The kind of local martingale term is actually always very much smaller, so you don't really feel it.
I have one question. Well, there's this broad conjecture, I think, that's for critical percolation. If you resample with probability epsilon, then the macroscopic thing should be independent. You already explained a bit why this is difficult, but for example, what is the special role of the 1/4 3/4? Why don't you?
No, I could put like any distribution sample at 1/2, but I just wanted to just convey like a concrete example.
Okay.
I could have taken like a random, like any even a constant distribution or something. Center at 1/2, it's fine.
So are there other obstacles?
Well, I think no, I think the main obstacle we found was really like this kind of rescaling, like this kind of using scaling relation, which should hold at all scale and try to avoid an analysis where you want to play kind of scaling relation, but say, okay, it breaks a bit here, a bit there, but it's not going to be that complicated. And it becomes scaling relation is already difficult because there are those exploration processes. But if you keep on top of that, like exploration processes with like forbidden boxes, it might be very difficult. Yes.
Where you are defining the FK percolation. So is the partition function, is it finite? The graphs, are they? Oh, the graphs are finite.
The graphs are finite, yes.
Fine.
But
Okay.
that's not trivial to pass to the infinite volume limit.
Okay. And the convergence in distribution to SLE, is it a finite dimensional convergence, or you are proving tightness as well?
I think like RSW estimate proves you the tightness for the family of curves. And then, I mean, you just identify the drifting term in the Lovener equation for the limiting process. You just identify it.
Okay, if there are no more questions, then let's thank Rémy again.